It's working out the basic error correction properties, the distance, the logical operators, stuff like that. I guess I didn't, did I explicitly ask you to say what the distance was? It kind of implicitly comes out of the statement of the logical operators. Yeah. Yeah. Okay. So, are there any questions on what's been happening so far? I have a question. Okay, there, good. Talk. Okay, so in that case, let's get started on today's topic, which is going to be quantum cryptography and quantum key distribution. So, so we talked about cryptography a little bit already last week in the context of Shor's algorithm and RSA. So let me kind of recap the basic idea of cryptography, which is that Alice wants to send a message to Bob, but there's an eavesdropper, Eve, that can see their transmissions. And they want to rank things so that Eve doesn't actually learn what the message is that Alice is sending. And so the way I talked about doing that last week was using something called public key cryptography. But there's other methods as well that I alluded to of private key cryptography. So in a private key crypto system, actually that's kind of simpler than public key cryptography, because in that case, Alice and Bob share the same key. Whereas in the public key cryptography, they have different keys. It's asymmetric. And the public key cryptography that we talked about last week, RSA, is only computationally secure, if that. Meaning that it's only secure if Eve has limited computational power. And of course, as we saw in the case of Shor's algorithm, if Eve gets a quantum computer that maybe increases her computational power and potentially lets her break a system that might have been secure against kind of reasonable classical eavesdroppers. So there's a further problem with computational systems, which is that we don't know how to prove that any kind of computational problem is really hard, right? We can't even prove that P is not equal to NP. And so what that means in practice is that cryptographers will say, well, OK, we think this problem is hard, and therefore we think this cryptographic system is secure. But the only way we really know that it's hard is that we tried a long time to break it and we couldn't figure out how to. I mean, I'm quite serious. That's like the main. I mean, there's occasionally some slightly stronger statement you can make, but that's the main method that people can look at and say, this is why we think this crypto system is secure. And of course, there's work going on, in the NSA and various spy agencies around the world of people also trying really hard to break them, but they don't publish their findings. So it's possible that one of them has already broken RSA or some other crypto system in widespread use and didn't tell anybody because they want to read the messages that are being sent.
So can we learn how to build a tinfoil hat?
Well, so the tinfoil hats will come in a little bit. Yeah, So in fact, most cryptographic systems that people use, even the private key symmetric crypto systems, do rely on this kind of computational assumption. But actually, there's a cryptographic system that doesn't. And that's even a classical cryptographic system, and that's called the one-time pad. Maybe I should say before getting into this, people have come up with other kinds of assumptions that you can make, like maybe Eve has kind of limited storage. So let's generate huge public random number. And nobody can keep track of this whole random number. It's just being generated at such a high rate. And people say, well, I don't know, maybe you look at the low bits of the microwave background radiation or something like that. And you're assuming that Eve can only store part of this number. and using that kind of assumption. But of course, memory is relatively cheap, and the NSA has huge data centers where they try, in fact, to store huge, huge, huge amounts of data. So, any kind of assumption that you make like that is just an assumption, and it may not be valid in the real world. Now, in the one-time pad, you don't have to make any kind of assumption like that on the strength of the cryptography. So the way it works is, so this is a private key crypto system. So Alice and Bob share some secret key K. And I'm going to assume that this is n bits long. And by secret, I mean that Eve has no idea what it is. So it's completely random from her point of view. Yeah, OK. And so then in order to encrypt a message, so Alice has an n-bit message M that she wants to send. And so she encrypts it by taking the bitwise XOR with the bits of K. So the ciphertext E is going to be M XOR K. So I take the first bit of M and XOR it with the first bit of K, the second bit of M with the second bit of K, and so on. Right? So for instance, if the message is 0101 and the key is 0011, sorry, so then we would get, for the encrypted message, well, the XOR is 0 and 0 is 0, 1 and 0 is 1, 0, 1 is 1, 1 and 1 is 0. OK, so this would be the ciphertext. And then to decrypt, Bob simply does the same thing again. He takes, so given the ciphertext E, he takes E plus K. And of course, since E is supposed to be M plus K, this is M plus K plus K. And in binary arithmetic, when you XOR twice with the same thing, that cancels. 1 plus 1 is 0. Everyone knows that. And so that's the original message M again. Right? As you can see in this case, you take the XOR here as 0, 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1. OK? And so the reason this is secure is that K is completely unknown to Eve and is totally random. And so that means that this message E, this ciphertext E, could be any bit string at all, no matter what the message is. Okay? And no matter what the message is, when you average over keys, all of these ciphertexts are equally likely. Okay? So if Eve sees the ciphertext 0110, she doesn't know if she got it because the message was 0101 and the key was 0011, or if the message was 1010 and the key was 1100, or any of the other possibilities, all equally valid from her point of view. Okay? So she learns nothing at all about the message. And so this scheme is what's called information theoretic. It has what's called information theoretic security. So Eve's information, when she sees the ciphertext about the message, is no bigger, no matter what, than her information before she saw the ciphertext, before Alice sent anything. OK. But I don't want to imply that this is completely without assumptions. There's a couple of assumptions here. So one of them is that Alice and Bob have their own kind of private domains that Eve can't look in, right? Because if Eve is looking over Alice's shoulder while she's typing her message, then any kind of encryption is not going to help. And similarly, if she's looking over Bob's shoulder. I mean, you laugh, but this is actually, in real life, this is how people attack crypto systems, right? I mean, there was recent news about Lenovo computers that they installed some sort of ad software in the operating system to break encryption, right? So they didn't have to care. They didn't care what crypto system you used because they were attacking it when it was unencrypted in your computer. Okay? And so this is where the tinfoil hat comes in to protect your domain so that they can't read your mind and see what messages you're sending.
Yeah, then I say just going to beat you up anyway. So.
Well, maybe. Anyway, so the upshot, though, is that the one-time pad makes this intermediate region completely secure. Okay? But in order to do that, well, you need the private domains, but you also need this long secret key. And it's important that the secret key be as long as the message. And in fact, you can't reuse it. Because if you reuse it, then you can say, well, I have 2 messages. I put them together, so that's a message of length 2, and I'm only using an n-bit secret key. Okay? So now it's not true that all pairs of messages, pairs of ciphertext, are equally likely. Right? And in fact, there was a historical case during the Cold War where the Soviet Union, they had these one-time pad code books, and they accidentally printed some pages twice. And the US was able to use that, the US NSA was able to use that to break some of these messages. Okay, so this is a real failure mode that can happen if you're not using the one-time pad right. So how do you set up the secret key? Well, either Alice and Bob have to have met in person before and exchanged the secret key and then gone off their separate ways. Or they have to have some trusted courier that will travel from Alice to Bob and give a secret key and transfer the secret key. If they try to send the secret key over the internet or phone lines or something else, that could be intercepted because we're assuming that Eve can intercept communications like that. Okay. And of course, once they set up the secret key, they're constantly using it up. Every time they send a message, they're using up part of their secret key. And so if they want to send a lot of messages or very long messages, then they'll run out. And then they have to meet again or send another courier to re-key them. Okay? So this is one of the reasons why computational security is more attractive. So if you have a computationally secure symmetric crypto system, well, you can use the same key for much, much longer. And usually the thing that limits how long you can use a computationally secure key, well, there's a couple of things, but one of the main ones actually is increase in computational power. So you set up a key at some point in time, but maybe people have been able to spend long enough working on their computers to try to break that key. Computers are more powerful now, right? And so maybe the old key, you don't feel it's secure anymore. It's also possible somebody broke into your computer and stole it during the intervening time, stuff like that. But you don't have to worry about kind of sending too many messages, generally. And moreover, you can, once you're in the realm of computational security, you can go to these public key crypto systems like RSA. And RSA doesn't require that you met before. It doesn't require you to send a trusted courier. Because the encryption key, the public key for RSA, can be made public. You can post it on your website. You can put it in the footer of your email, like PGP. And the way it actually works in the web, the secure connection, is that when you first connect to the website, then you say, please send me your secret key. Okay? Or your public key. Obviously not your private key. Your public key. And you get that, and then you can start an encrypted session with them. Okay?
What?
Yeah.
How long are the strings usually used in RSA? Like 250 bits?
Yeah. So there's various. No, they're longer than that actually. So the RSA, I mean, you can use whatever length you want basically, but I think the recommendations now for RSA are like well over 1,000 bits, 1024, 2048, maybe even longer by now. The number that you're thinking of is remember I said that RSA is just used to kind of set up this private key crypto system. So that's the length of the private key that gets used in the SSL protocol.
So, I mean, surely if it's only like factoring a 1,000-bit number, surely that can be done like on a supercomputer kind of given a few days.
No, no. Because remember, it's something like 2 to the n to the 1/3, where n is the number of bits. Okay, and I don't remember offhand the largest numbers that have been factored, but they're in the hundreds length. Mm-hmm. Okay, and you need a big cluster and months of computation time to do that. Now, it's true that kind of RSA keys from maybe the 1990s are something that you could do much more easily nowadays. But today's RSA keys, they have to be longer because, I mean, it's an arms race, right? As the computers get bigger, you make the key longer. But the point of exponential security is that you don't have to make the key much longer to be much more secure. If they're both taking polynomial time, then it's kind of a much closer race. OK, so this is the one-time pad. And now we're going to move to quantum cryptography. This is purely classical. And quantum key distribution is a method of sending quantum states to kind of solve some of these problems with the one-time pad. So if Alice and Bob can know that so OK, let me start drawing stuff. So in quantum key distribution, Alice and Bob are going to have a quantum channel. Okay, and Eve can interfere with this quantum channel. She can take qubits out of it. She can change qubits in it, whatever. And they also have a classical communication channel. And this classical channel, Eve can read it, but she can't change it. Okay? And I want to make that assumption so that Alice and Bob know that they're really talking to each other. So I'll get back to that towards the end. But because Eve can read the classical channel, they're still kind of in this realm of classical cryptography where they can't send anything secret over the classical channel because Eve will be able to read it, unless it's encrypted somehow. And so in quantum key distribution, which is almost always abbreviated QKD, Alice and Bob are going to set up a secret key. And they do that by sending quantum messages over this quantum channel and then doing some kind of checking and comparing over the classical channel. And the point is that they don't need to have shared any prior key, except to the extent that they need it for this classical channel, which I'll talk about in a minute, or more than a few minutes. But before the end, I will talk about it. So Alice and Bob don't have to have met before, right? So they could be just kind of new people that just want to talk to each other and establish the secret key. And moreover, whenever they run out of key, they can use this method to generate more key. So it kind of incorporates some of the main advantages of public key classical crypto systems. It doesn't do everything that a public key system can do, but it covers a lot of the same grounds. And the advantage is that it's information theoretically secure. I mean, assuming you believe in quantum mechanics. And actually, there's kind of variants of it which are secure, even if you don't really believe in quantum mechanics, but you believe that there's no faster-than-light communication. But that's a bit harder to achieve in the lab. Maybe I should say on that note that quantum key distribution actually is something that's fairly practical at the moment. I mean, there's companies that are selling real QKD systems. And it's something that's been done experimentally many, many times. There's some kind of limitations to it, which if I have time, I'll discuss at the end. But but basically, it's a kind of a practical thing, albeit one that's not yet widely used. OK, so how does this work? Am I going to fit on this? OK, let's try. So the kind of best-known quantum key distribution protocol is the first one, the BB84 protocol, invented by Bennett and Broussard. And so in this BB84 protocol, it's going to rely on Alice sending one of 4 states to Bob for each qubit, for each kind of raw qubit. The first step is Alice generates a number of random bits. OK, so that's not hard. And then the thing is that each of these bit pairs is going to specify a qubit value. So AI is going to be the basis. And Ri is going to tell you which state you have within that basis. So if AI is 0, Alice is going to use the Z basis, the eigenbasis of the Z operator. And so she's sending either 0 or 1. And if it's the 1 basis, then Alice is going to use the X basis, the eigenstates of the X operator. And so she's sending plus or minus. Now, of course, in practice, you're going to send these almost always using photons. And so you want to use some photon states. So for instance, if you use polarization, these could be horizontal, vertical basis or diagonal basis. Or you can use some other degree of freedom of the photon, like a time bin or something. If it's early or late is another possibility. Or some superposition of those. OK, so the next step then, of course, is that Alice is going to send these qubits to Bob. Now, Bob receives these, and as he does, so Bob is going to choose n random bits. Sorry, well, yeah, so the bits are BI, and these BIs are going to specify the bases. And so he measures qubit I in basis BI. And when he does so, he gets some measurement result, which is a bit, which I'll call SI. OK? So Bob picks BI equals 0. He measures in the Z basis. If he picks BI equals 1, he measures in the X basis. OK? So so the next thing, so notice that sometimes Alice is sending AI, sending bits in basis AI, which she chose at random. Bob is measuring in basis BI, which he chose at random. They didn't compare notes ahead of time. So sometimes AI and BI are going to be different. And then, well, if Alice sends in this basis and Bob measures in plus minus basis, he's just going to get a random result. Okay, so that's not really valuable for them. So they didn't compare ahead of time, but they compare after the fact. So Alice and Bob are going to use their classical channel and reveal what bases they used. And they discard any bits for which the bases are different. And the ones they keep are the raw key. So why is that? Well, so when the bases are different, as I said, the results are random and uncorrelated. But when the bases are the same, if there's nothing else going on, then the bit result that Bob gets could be the same as the RI that Alice sent. Okay? And so in the absence of anything else going on, any eavesdropper, any noise in the system, Alice and Bob have their shared secret key. Okay? But the reality is not so simple. Okay? So first of all, because we're thinking of this as a real system, they send it over an optical fiber or something. There might be some noise in the system. Maybe the photon got lost and got replaced by some dark count or some stray photon. Maybe the polarization got rotated, something like that. And so even in the absence of an eavesdropper, it could be that Ri is not equal to Si. Okay, so they're going to have to deal with that. But moreover, there could be an eavesdropper, right? And the eavesdropper might try to measure some of these qubits as they're sent in order to figure out what's going on. The thing is that because they don't announce what their bases are until after Bob has already received the qubits, Eve, when she has access to the qubits, when they're on the way from Alice to Bob, she doesn't know what the basis is. Okay? So if she wants to try to make a measurement to figure out what the bit Ri is going to be, she also has to guess about the basis. Okay? And in doing so, she's necessarily going to introduce errors of her own. So for instance, imagine that Alice sent the qubit 0. Okay? Now, if Eve happens to measure in the Z basis, she'll get 0, and she'll know what the qubit is. But if Eve guesses wrong and guesses in the plus-minus basis, the X basis, then she gets some result at random. Say she gets plus. Well, she wants to fool Bob. She wants to make Bob think that there's nothing happening. So she sends this plus on. She can't measure Alice's state and also keep a copy of it, right? That would be cloning. So she has no choice if she measures it to try to make a new state to go in its place, so that Bob will think that everything is okay. Bob, when he receives the plus state, well, he also has to pick a basis to measure in. Now, if he happens to pick the X basis, it doesn't really matter because they're just going to throw out that bit anyway. So let's consider the case where Bob measures in the Z basis. But the thing is that Bob has a 50% chance when he measures plus, has a 50% chance of getting 0, which is right, and a 50% chance of getting 1. So there's a 50% chance of an error. Of course, even if Eve is doing this attack, Bob is not going to have errors in 50% of the bits. He's only going to have errors in 25%. Because half the time Eve is guessing the right basis. In that case, she's sending on the correct state to Bob. Okay? So the point is that Eve, trying to eavesdrop, introduces errors into the system. Okay? And that's something that Alice and Bob can, in principle, detect. So that's what they're going to do. So Alice and Bob will choose some subset to announce of their raw key, to announce and compare. Let's say 50%. And so they calculate the error rate. And they'll abort if it's above some threshold value. Abort if it's too high. So they have to look at their security proof for this whole system to figure out what too high means. It depends on some of the details of the system. But in a kind of an idealized case like this, I think it's roughly 20% they can achieve. Although to do that, they have to give up a lot of their bits that they're sending. So the thing about this is that what quantum key distribution does, it doesn't automatically generate a secure key. Instead, it lets Alice and Bob detect the presence of an eavesdropper. Okay, so an eavesdropper, of course, if all she wants to do is some sort of denial of service, she can just do lots of stuff and make lots of errors, and Alice and Bob will always abort. They'll be unable to use quantum key distribution. But what quantum key distribution protects you against is Eve learning the key without Alice and Bob knowing that. Okay, so if Eve is sometimes eavesdropping and sometimes not eavesdropping, Alice and Bob try to generate a key, it doesn't work, and then they say, okay, let's forget it for now, let's try again later. And then if they manage to pick a time when Eve is not there, the error rate should be lower, and they can succeed in generating a key that is then secure. Moreover, it gives Eve kind of a choice, right? Because Eve can choose to eavesdrop a lot, in which case she learns a lot about the key, but she's going to get detected, almost certainly. Or she not do very much. Doesn't learn very much, but doesn't cause the protocol to abort. Alice and Bob go through and generate the key, but then she doesn't know very much about the key. And in the final steps, we're actually going to convert not very much about the key into almost nothing. Okay? But before I do that, does everyone kind of understand what's going on so far? Yeah.
So the protocol above, like the classical protocol, the keys have to be identical. The keys have to be identical on both sides in order to
Right.
reach the code.
That's right, yeah.
If there are like any errors, you won't get the message.
Right.
And here we can have errors introduced by Eve and by the environment.
Right, right. So you're right. So we're going to have some way of getting rid of those errors.
50% of them you're sharing, and you can see, oh, those are wrong. But there are some that.
Yes,
Okay.
absolutely. So you're completely right, and that's step 6.
Okay.
Yes.
Well, I guess let's go through step 6.
Okay. Yeah.
So this protocol prevents from man in the middle attacks. I mean, if pretending it to be because of. So that's.
Let me get back to that at the end.
Okay.
So that's an important point, but that's basically it's the classical channel I said was.
Two ways, right?
Well, it is 2 ways. It's going Alice and Bob, but Eve can read it but not change it.
Okay.
It's an authenticated channel. Yeah.
Yeah, Ilan's question raised a question of my own. So there's some form of sort of, if I call it an information hierarchy, in the sense that if you wanted to send a message, the message would originally be, say, in a language, in a human understandable language like English. Then you encode it into classical information.
Right.
And then you could use some quantum system to encode or to encrypt or transmit this information. So I guess my question is, how much of error correction that happens at the human understandable form translates into your physical system?
Yeah, so normally the types of protocols that I'm talking about, you're going to try to do error correction and all that other stuff perfectly, or essentially perfectly. And I guess there's a variety of reasons for that. One is we're treating this at a theoretical level, so that's kind of the cleanest theoretical situation. At a practical point of view, if you said, well, OK, I can tolerate some noise because it's natural language and there is redundancy there that people will be able to correct. Different people might be able to correct different amounts of redundancy, and you don't really know what the right amount is. That's OK. And furthermore, a lot of communications that happens nowadays is actually computers talking to other computers. And they have much less tolerance for correcting typos and whatnot. So, I mean, if you're getting a web page, right, it's an HTML document that has to be parsed by your computer. If it can tolerate some irregularities in it, but it is kind of sensitive to even single character changes. So those are all, I think, good reasons to just say, let's try to correct everything. I mean, there's always, if it did start as natural language, there's going to be additional ambiguity from, people being unclear in their message. So you might as well try to get everything else that you can to be correct. OK, so maybe then let's move on to the error correction. So in order to do error correction, Alice and Bob now have these 2-bit strings. In the ideal case, they should be the same. But in the real case, there will be some disagreement between them, okay? Which they know is not too high because they compared. But nevertheless, they want to get rid of that. So what do? Well, basically, they want to apply some error correcting code, except that they've already transmitted. I mean, Alice has kind of already transmitted this thing to Bob. And the thing that Alice has is just random. But what they can do is they can take the parodies. So you remember yesterday I mentioned these classical linear codes are generated by a parity check matrix, which is defined by the parodies of certain subsets. And so what they're going to do is Alice and Bob will take the parodies of those same subsets corresponding to some classical code. And they announce those parodies and compare them. Okay? So the parody, again, if the bit strings are the same, the parody of some subset of them should be the same. Whereas if an odd number of bits have been flipped in that subset, then the parodies will be different. Okay? And this is exactly how the error correcting code works. So by choosing the parodies corresponding to an error correcting code, they can figure out which bits disagree and correct them. However, in the process of doing that, they've announced some number of bits, right, which are the parodies of these things. That gives Eve some additional information about the raw key. So they have to discard 1 bit for each parody that they announce. So this is one reason not to use this protocol when the error rate is very high. When the error rate is very high, they have to discard a lot of the bits just to do error correction, and they won't have very many left. Yeah.
How can you distinguish Eve from the environment?
You can't.
Right.
That's the point. So if the error rate is very high, well, then, I mean, again, you don't know if it's Eve or it's just there's something bad that happened to your system to make it so noisy. But either way, you can't trust it, and you shouldn't use it. If the error rate is low, well, maybe it's just natural errors. Maybe it's really Eve. But either way, you're going to, in the next step, be able to get rid of any information that Eve might have in that case. But the point is that at this step, you just want to correct the thing so you have the same bit string.
Does that? I mean, I understand that would get rid of
No, this is not getting rid of any of Eve's information. This is getting rid of the errors, so they have the same bit string.
Right.
There's step 7, which I ran out of space, but I'll write it in a minute.
So, do they share all the parities for their string?
They share the ones that are the parity checks for this error correcting code. Okay, so the number of those is less than the full length of the string.
Right, but okay. My question is: do they have to share the parity of the first bit and the second bit, and the second bit and third bit, and third bit and fourth bit?
Oh, yeah. So if they were using the repetition code, then that's what they would do, right? They would say, what are the parity of the first 2 bits, the second and third, the third and fourth, and then there would only be 1 bit left, right? Because they're using all but 1 parity. But for more sophisticated error correcting codes that have a better rate, then the number of parities can be much less than the total number of bits, and yet they'll still have many bits left over. I mean, so they'll still have many bits left over, but they can also correct many errors. Okay, so I didn't really tell you about codes like that, but they exist.
And can I ask one more?
Yeah.
So when they discard a bit for each parity they announce, I guess they have to agree via the classical channel in which bit they.
Yes, so they can do that via the classical channel. This part, actually, they could agree ahead of time which parities they're going to use.
Okay.
This part, that's OK. Some of the, I mean, like, when they're deciding which ones to announce and compare for errors, those they can't decide ahead of time. They have to be, because anything that they decide ahead of time as part of the protocol, you have to assume that Eve knows what that is. Okay? But anything that happens during the protocol, after Eve has already interfered, then Eve doesn't necessarily know. And the thing is that if Eve knows which bits they're going to look at to see what the error rate is, then she just won't touch those bits, and she'll only attack the other ones. So that's something that has to be said later. This, though, doesn't have to be. It can be earlier. Yeah.
So at this point, if Eve has been eavesdropping the whole time, what she knows about their code is only the bits where all 3 of them took the same basis, right?
Well, OK, so first of all, she knows the ones that they announced and compared.
Sure.
Whatever she did.
But presumably they're going to throw those out afterwards.
That's right. Yeah. So it's not valuable to her. She knows the parities of various sets of bits because of this. But again, because they're throwing stuff out, that's not going to be valuable to her, right? So if she knows the parity of bits 1 through 4, but bit 4 is no longer being used, and she doesn't know what bit 4 was, they just threw it out, right? That's not helpful to her. Right. Okay. Now, exactly what else she knows depends on how she chose to attack the system, right? Because if she's making a kind of a maximal attack where she measures everything and learns as much as she can, then they're going to abort, okay? And they're not going to even get to step 6. Okay,
but
so
assuming that they do make it to step 6.
Then she's done something that's less intrusive, but learned less information.
Right.
So exactly what she knows depends on exactly what she chooses to do.
And if they're going to end up, if they're going to end up doing the one-time pad with this code,
Right.
that is what they do. Right?
Yeah.
How useful is it to her to have a quarter that's replicating?
Well, potentially very useful. I think I gave the example last week of suppose Eve has narrowed it down to 2 possible messages, right? We're going to meet at noon or we're going to meet at midnight, right? And then if it's just the bit that she happens to get is the one or the couple of bits that happen that say noon or midnight, right? Then all the other stuff in the message she doesn't really care about because she knew that already.
And if she already knows it's one of those 2, she doesn't even get the whole word. She can just get like, N-O, and it's like, oh, it's new.
Right, that's right. Or even just the first letter, right? So potentially quite a lot. If she learns even a few bits, that could be bad. Okay. Now there was one more question, I think.
No,
you're done. OK. So how do we get rid of that possibility? And so that's the last step, which I guess I can put under here, which is called privacy amplification. OK, and so in privacy amplification, Alice and Bob are going to try to wash out whatever information Eve has about this string. So what they're going to do is they're going to choose random subsets and take the parity. So they don't announce these parities, unlike the previous step. They keep them secret, and in fact, the parities become the final key. Okay, and everything else is discarded.
They do announce which subsets.
They have to announce which subsets because they have to agree on them. And this is, again, something that could be chosen late. That is not part of the protocol. It's something that has to be chosen at random so that Eve doesn't know ahead of time which subsets they're going to pick. So the intuition here is, again, kind of the same as what I said before. That suppose they say, oh, let's take the parity of bits 1 through 10. And that will be the first bit of our final secret key. Now, if Eve knows all 10 of those bits, she knows what the parity is. But if she only knows 9 of them, and the last one is random, she has no idea. It's completely random, the parity. Okay? So this is why parities are good, because they're very sensitive. And so Eve has to know almost everything to have even she has to know a lot about every one of those bits in order to have a reasonable chance of guessing what the parity is. So at this stage, even if Eve knows a few bits of the key, it'll be gone. She'll know her information will be like a very exponentially small fraction of a bit. Even if she knows a significant fraction, in fact, of the bits, you can get rid of them using this privacy amplification. Yeah. So yeah.
Are they choosing the random subsets over the classical channel?
That's right. Yeah. Yeah.
And so Eve might even know what those are, but she doesn't have every bit in the subsets.
Well, she doesn't know ahead of time what they are.
Right.
But once they're announced, I mean, they have to compare so that they're picking the same subsets. Otherwise, they'd be introducing errors again. And so Eve definitely will know what those are.
And so they'll say, all right, we'll take the parity of bits 1, 5, 7, and 9. Eve's crap, I only have 1, 5, and 7.
Exactly. Okay. Right. Yeah. So the final upshot is that you get the following security condition. Well, this is a kind of a hand-wavy version. So the security condition says that for all attacks by Eve, well, Eve has a choice. Either she can do something that is kind of very intrusive and learns a lot of information. But in that case, she is caught with very high probability. And by high probability, I mean exponentially close to 1. Close to 1. Or she does something that's not as intrusive and is not going to set off Alice and Bob's alarms. But in that case, she has, again with high probability, almost no information about the key. And by almost no information, I mean an exponentially small amount. That's much less than 1 bit.
How can you have less than 1 bit of information?
Well, yeah. So I haven't really talked about how to quantify information.
Okay.
But for instance, one way that maybe seems reasonable is to say, well, I think this bit is 1 with probability 1/2 plus 2 to the minus 100, and I think it's 0 with probability 1/2 plus or minus 2 to the minus 100. Okay, and it's actually, well, whichever one it actually is, clearly I have very little information about it, right? Because I can't guess much better than I have. Okay, so I'm not gonna make this more precise, and I definitely don't have time to get into a security proof of quantum key distribution. But there exist security proofs. There exist many security proofs. This is just one quantum key distribution protocol. There's a bunch of others, quantum key distribution is kind of this whole big field by itself. So let me then see if there's any questions on the protocol, the security condition, and then I can get into that earlier question about the man-in-the-middle attack. Yeah.
What about, sorry, one second. What kind of things would you want for, say, like another security protocol over this one? Like, what are important features in choosing one over the other?
Oh, I see. One of the other QKD protocols.
Yeah.
Okay, so one factor that certainly you're interested in is how high rate can you generate key bits at, and compare that. There's a trade-off with what error rate you can tolerate before you have to report. Okay, and so different protocols kind of have different trade-offs in there. I mean, this is maybe not a big deal because these are all exponentially, but you might also have kind of different levels of security that, they're exponentially secure, but maybe the security, but it's different exponential rates, right? And so if you really want to very, very secure, you might insist on one or the other. That's usually what happens is you kind of fix the security, and then you do what I was saying about what's the data rate, what's the error rate that you can tolerate. An important factor is how it interacts with your implementation. So like this BB84, you have to be able to generate these 4 states. There's another protocol, B92, that uses only 2 states. Okay, and so for some experiments that's easier because you only have to switch between 2 states. But it has worse error tolerance and stuff like that. Then you can try to get kind of extra properties of various kinds. So for instance, I mentioned earlier that so this protocol, you can prove security under quantum mechanics conditions. Now, there's some issues if Alice's devices and Bob's devices don't work exactly right, which will always be the case. And I think we'll explore one of those in the tutorial tomorrow. But you can make it secure kind of under reasonable assumptions. But people have also looked at something called the device-independent quantum key distribution. And that uses entangled states. And it turns out that if those entangled states are violating Bell inequalities, then basically you have to make almost no assumptions about how devices are behaving, provided they're not explicitly leaking information about the key. And another nice thing about new protocols, it seems like the device-independent ones should even be secure if quantum mechanics is wrong. And this is what I mentioned earlier, provided there's no fast and light communication, right? Because Bell inequality violations means there's no local hidden variable that describes what's going on. And Eve's knowledge is a local hidden variable. Okay? Now, if you have fast and light communication, then you're kind of more in the realm of non-local hidden variables, and of course it doesn't work. those proofs are not complete. I mean, the device independent that work kind of regardless of what Alice and Bob's device are doing, that seems to be solid now. In the case where, in some theory beyond quantum mechanics, well, there are some proofs, but the security is not as good. So but intuitively, it seems like it could work. But of course, you don't know what the theory is, so it's hard to put too much stuff down. Okay, so properties like that. Yeah.
So we're using that key for one-time pad, right? Or you doing?
Yeah. So once you generate the key, well, you can use it for any kind of cryptographic protocol, but in particular, you can use it for the one-time pad.
So the one-time pad keys should be as long as the message.
Mm-hmm.
And here we're already throwing away lots of bits.
Mm-hmm.
So it seems like we'd need a huge key to send.
Yeah.
Much
that's
longer
right.
than.
That's right. So that is one of the practical drawbacks of quantum cryptography is that while in principle you can generate arbitrarily many key bits this way, in practice the rate at which you can do this is kind of much less than the rate at which we send information nowadays. And so that's one of the reasons that it's probably not widely used in practice. But if you have some subset of messages that you really want to be very secure for, and you're willing to cut those down in size, then this is maybe a good thing to do.
Can you,
Sorry, if I can pass it. Let's start again.
Okay, maybe this is going to be answered in a minute, but how realistic is the assumption that Eve cannot act on the classical channel?
Yeah, so that's the thing I wanted to get back to.
Okay.
Yeah.
So for a reasonably sized message, how long does this protocol take?
Yeah, so there's lots of different implementations. I think that the fastest ones are now up to like a gigabit rate of key generation over probably some limited distance, which is not bad. Not bad.
Gigabit
per
second?
Yeah.
Good.
Yeah, I could be wrong, but I think that's right.
Is there problems with
But that's probably only a very limited range and kind of only under very good conditions. I mean, people have talked about, for instance, using QKD from ground to satellite, and that's going to have much lower. I don't know if it's been done; it hasn't been done publicly, but that's going to have much lower rates. I mean, if you'd be lucky, probably you get a kilobit per second.
Yeah, can you using something like this method to send a random key, and then rather than using that for a one-time pad, using it for AES or something that's a bit more.
Yeah, and in fact, that's kind of what some of the manufacturers selling this thing suggest that you do.
Right.
That you use a computationally secure system, but you change the key frequently.
Yeah, right.
Which hopefully should give some additional security.
Right.
It's not clear how much additional security it actually does give, but.
Well, I mean, yeah, it means that they can't break it by comparing different.
That's right. So they have a limited number of messages to compare, and that does help to break it. But it's also the case that they can store it and then wait until their computers are better, and then spend a long time working on it, and eventually break it.
Yeah, right.
It doesn't protect against that. Yep.
I have the same question.
Okay. Okay. So then let's talk about the man-in-the-middle attack, which I swear is on my notes. So the man-in-the-middle attack. So here we have Alice is trying to send stuff to Bob, but there's Eve is intercepting everything she sends, and then we have this classical channel, but Eve is intercepting that as well. And everything that Alice sends, she thinks is going to Bob, but actually is going to Eve. And then Alice receives classical messages back saying, oh, I measured in basis x, z, x, x. But actually, those are coming from Eve. Okay? And then moreover, Eve can run the same protocol, pretending to be Alice, and talk to Bob that way. Okay? And so then Alice and Bob will generate some secret key. And Eve and Bob will generate some secret key K prime. And Alice and Bob both think everything is fine. They've gone ahead, they've run the protocol, they've generated a secret key, but it's not shared with each other, it's shared with Eve. And then when Alice encrypts using the one-time pad, well, then Eve can read it, and then she can re-encrypt it and send it on to Bob. So even after Eve has intercepted the message and read it, Alice and Bob still don't know there's anything wrong. So this is called the man-in-the-middle attack, and it's a potentially serious problem. And this is why I assume that that the classical channel that Alice and Bob were using was what's called authenticated. So now I can say that in RSA, you have the same problem, right? Because suppose you go to a website and say, please send me your public key. Okay? Well, somebody sends you a public key, but unless you really know it's from that website, it's not really helping you, right? Because it could be that it's Eve that's in the middle that sent you the public key, and you're encrypting to her, and then she's reading that and re-encrypting it with the actual public key and sending it onto the website. So the QKD is doing the same thing in that respect as RSA. It's turning an authenticated channel into a secure channel, an encrypted channel. Okay. Now, there's various possible solutions to this problem. How do you get this authenticated channel? So the one that's kind of the most secure and most compatible with QKD is, so if Alice and Bob have a prior secret key, then they can use that to do an information theoretically secure authentication, classical authentication. Now, and actually this worries you. I'm saying, well, assume they have some secret key and then they'll use it to make secret key. But luckily, authentication uses much, much less secret key than encryption does. So encryption, you needed 1 bit per bit of the message. Authentication, you need more like log of the size of the message. So if this is what they're doing, well, they do have to have met before in order to get the secret key in the first place. But once they have just a little bit of secret key, they can use quantum key distribution to expand that secret key, to generate more secret key. So that's one way you can use QKD. Yeah?
How do you go through that? How does the authentication process work?
Yeah, so I don't want to go through the details, but the basic idea is you'll take the message that Alice wants to send, and you'll calculate some hash of it. Okay? And yeah, usually you calculate some hash of it. So that's maybe again take some parities of subsets, and then you'll compute some function of that hash and append the output of that function. And the thing is, this function is chosen from a family of functions. And the family is indexed by a secret key. Okay, so the thing that's supposed to go along this authentication tag is you can see it, but you don't know what it's supposed to be, and it's unique to the message, or at least to the hash message.
So do you encrypt everything using this?
Well, it's not encrypted, right? The message is still sent in plain text, but there's something short that's appended. So here, a very simple example. I have a long message, and we've agreed ahead of time that I'm going to take the parity of some subset of the bits of this message and send that as well. Okay, so I send the whole message, and then I send this one extra bit. Okay. Now, we know which subset we're going to take. Okay, but Eve doesn't know which subset we're going to take. That was what was specified by the secret key. And so Eve can see that this particular message has a 0 associated with it. But then if I send some other message, well, we're not going to use this key again. But the point is that
Yeah, right.
he doesn't. There's a lot of different ways. So if he wants to send a different message, he wants to change it, he doesn't know which parity, and it might be that it would cause the parity bit, the extra bit to flip. Okay.
Right.
Obviously, one extra bit is not very secure. You send more than that. But that's the basic idea.
But that's not what she's doing in the middle attack. She's sending the exact same message to
No, that's not true. Okay, so Alice is generating random qubits, sending them to Eve, and Eve is making some basis measurements and sending them back to Alice. But Bob, when he receives the qubits, is making a totally different set of basis measurements. Okay. So Bob is saying, oh, I measured x, z, x, x, z, but Eve did something different. She measured z, x, z, z, x. Okay, and so she would have to change Bob's message in order for that to work. And if she can't measure the same things as Bob, because she doesn't know what Bob is going to measure yet, right? She hasn't sent anything to him.
So this is an explicitly quantum authentication protocol.
No, this is a classical authentication protocol. This is purely classical. And it's just that you want to use it with the quantum protocol to create the authenticated classical channel. Okay. Yeah. So let me just mention one or two other ways you could do this. So one way that doesn't require Alice and Bob. Oh yeah.
Sorry, very quickly. In the way that you have just described, is it that the quantum channel is feeding back into the classical channel? Unless
not exactly. I mean the feed. I mean there is feedback in that they're making some choices. They're getting measurement results, and some of those will get sent over the classical channel. But again, this authentication protocol is purely classical, and the messages in the classical one are, I mean, in some sense they're just random numbers. It's just you generated some of those random numbers by doing the quantum stuff. Is that fair?
Yeah.
Okay. So other ways you can do this authentication. So if Alice and Bob haven't met before, then one thing they might want to do is they might rely on some kind of mutual acquaintance to authenticate their messages, which could be a company that's their business. So then you have a shared private key with this company. You authenticate the messages to this company. The company says, yes, I can verify that it came from Alice, and then she sends it on to Bob, and Bob knows that it came from the company because they have a shared private key as well. Okay. Now they have to trust the company to faithfully send on the messages. But that's less trust than say, oh, here's our secret key, please pass it on. Okay? And in particular, you can rely on multiple companies if you don't trust this one. You can say, well, here's 5 different companies, and we'll ask all of them to authenticate the message for us. And then they all have to be cheating in order for there to be a problem. Whereas if you give them their secret key, even if one of them is cheating, they can have a problem. Although you can do the XORs. That's actually not an issue. But nevertheless, you're getting more trust. Then another possibility, which is to slightly give up this information theoretic security and say, well, I'll use a computationally secure public key digital signature to authenticate these messages. Now, of course, then you're vulnerable to computational attacks on the digital signature. But the thing is that once the protocol is over and you've generated the key, now it's too late. Okay, so you can't. I mean, Eve with public key encryption, Eve can keep it and say, "I'll try to break it later," and it takes months of computation to do that. But with the authentication, months of computation is too late. Right? She's lost her chance to play them out in the middle. So it's still only computationally secure, but you're still kind of upgrading the computational security to
It only has to be computationally secure for a short time,
Mhm.
and then it's information theoretically secure. Okay, so let me stop there since I've gone way over. But are there any last questions? Okay, then tomorrow we'll talk about more information for yourself.